Okay, let's get started. No one wants to learn about machine learning. Yeah, so so what I want to do for the next couple of weeks is talk about various machine learning algorithms we can do on Spark. Now, part of the problem with doing that is if you've taken the machine learning course, you know that there are a lot of details in each algorithm, and there's hyperparameters you can deal with, and dealing with that properly requires deeper knowledge than we have time for. But still, being able to now set up the workflow, run them, is going to be useful to know how to use Spark. And you know, we're starting with regression, linear regression, because it's a simple idea. I mean, just a line, right? And then we'll go on to logistic regression, which is slightly more complicated, but it allows us to build some more interesting models rather than just here's a line. You know, I definitely want to do some neural nets. I haven't decided whether to do decision trees or not. There's a whole list of algorithms we could do, but I'm still working on which ones we want to cover. Like I was telling people earlier, next assignment should be out tomorrow. It's a matter of, you know, what can we do on Spark? And I figured that out, and then I figured out, okay, what to do with that. Plus finding a data set where you can't find the answers online is becoming more and more of a problem. But I always like to use a movie data set because there's various sizes. So you can start small and then go to, you know, gigabytes of data, but those are sort of standard problems now that people have worked over, and so you just Google, you know, how do I so one data set we'll look at in assignment 4 is survival rates on the Titanic. So any questions before we get started? Also, last time we looked at some overview of, you know, machine learning library and Spark. Talked a little about linear regression. You know, basically we're trying to estimate data by plotting a line. Talked about residuals. We talked about Pearson's correlation, to sort of a physical measure of whether or not things are those two variables are related or not. And so I want to pick up there. You know, so how can we actually compute the Pearson's correlation coefficient? So here's an example I want to use. You know, I picked the simplest example I could, where it's just f of x equals x, right? And we have to convert that to a file so that we can read it in Spark. So I did that, no problem. And so we can just read the file in. Here, you know, doing a CSV, and I can infer schema, and it's going to infer that those are integers, which is fine. And then I can just, boom, right? And the answer is yes. I mean, we get 1. Remember, 1 means they're maximally related. 0 means they're basically random, right? And -1 means they're inversely related. So that's good. I mean, they're clearly related. and the measurement says they are related. We can also use an aggregate function. So there's multiple ways of actually computing this value. And then what I did is, well, let's try something that's obvious. And so I created a constant column and asked, are those related? And the answer was, well, a nan, right? Well, and that makes sense. Why? Well, because if one is the independent variable and y is a dependent variable, what we have is a vertical line, right? And so what expect to happen, right? You're saying you get multiple values from the same input. But also, if you've got a horizontal line, right, the Pearson coefficient can't deal with that either. So horizontal line or vertical line doesn't matter. So then I tried just creating a column of random numbers, right? And I like to do this because when you're dealing with, if you're a statistician or mathematician, right, you study these things, and if you study these functions long enough, deep enough, you gain sort of intuition of what they mean. But we're not statisticians, we're not mathematicians, right? So I like to do various examples just to see, what do we get, right? Because then we can build up some intuition just from examples. And so then what I did is when n was 10, we actually get, 0.1. And you can sort of see that in the sense of, well, if I start at 2, I can go to 2, then 4, then 5, and 6, and I get an increasing sequence, right? So you can start finding some patterns, even though it's random, right? It's a small enough data set. I did it a second time. Of course, you get different random numbers, you get different results. Go up to 20, it was negative. Well, but again, that just says it's inverse related. There's a smaller absolute value. When you start getting larger numbers, it slowly gets smaller and smaller to expect, because the more numbers you have, it's just going to be completely random, and you're not going to be able to find any trends accidentally, right? And finally, when I get to 500, now it's getting close to 0, right? And that's what you'd expect. It also points out that if your sample size is small enough, your inference is going to be not so great, right? And then I did it on some real data. So this data is looking at about 600 students that applied to San Diego State Computer Science Department over the years. Looking at their GPA that they earned once they graduated, and their GRE scores. And so we can then ask the question, how correlated are the grades you earn as a graduate student with the GRE scores? And when you do the GPA with a quantitative score, it's like 0.24. Well, looks like I copied the numbers wrong, but they're both the same, right? There wasn't much difference, so that was a little difference. They weren't exactly the same, so I copied and pasted incorrectly. Right, so there's not a real strong correlation between the grades you earn as a graduate student and your GRE scores. Well, yeah, I mean, first of all, the GRE scores have no computer science information at all, right? It's all generic. Secondly, we're looking at 3 numbers, right? How well do you think 3 numbers can accurately show your ability and what you've known?
See how beneficial quantitative field. But there's like a correlation between this, how well you're going to graduate. So
yeah, I mean, so it's yeah, it's not strongly correlated, right? And if you thought about it, you wouldn't expect it, right? And I wouldn't expect it in any field, really. But again, it gives us an intuition, right, of what that number tells us, right? And I always think the Indian students might be interested in this number, but they never are. So now let's move on to look at linear regression, right? So you want to be able to, input data and actually compute a model linear regression. And in Spark, the default is we want an independent variable or variables and then a dependent variable, right? They call them label and features. We can modify that as a default. When you do the model, it's going to look for a column called label, which is a dependent variable, and then a column containing features. Like I said, we can change it when we create the model to have other titles for the columns, so that's what they expect, right? And so you expect the label to be a double. I mean, the column to be double. And the key thing here in the feature is expect that column to be a Spark vector of doubles, not a scalar vector of doubles. And so then one question is going to be is how do we actually convert numbers into, right, a column of vector of doubles? So again, I use a simple example. I mean, we know what the answer is going to be, right? It's just so there is a format that is apparently commonly used for files. It's called SVM, and it comes from the Libsvm, which is apparently a popular machine learning library developed in Taiwan, and it's open source, and so a lot of the code's reused. And there's a popular machine learning library in Python called Skykit, which uses this format too. And the format is basically your label and then the space, and then for each dependent or independent variable you have an index and then the value space, another next. So could be like 1 value, 2 value, etc. Right? And so initially, the easiest way for us to deal with doing regression is to just convert our input file into that format. And we only got one independent variable, and so each data is preceded by one colon, right? And of course, it's sort of irritating to do this by hand, so we need some other way of doing it too, because when you have, the 10 values here, it was easy. If you've got 10 million rows in your files, I mean, you're not going to want to do it by hand. Now, when we do machine learning, usually you end up dividing your data set into 3 pieces. The first piece you want to train your data set, train your model on, and then you need another piece that you can use to test it, right? And your test data, you want to have the same distribution as your original data set to see what still works. So you know that if it doesn't look well, there's a problem with the model, not that you have 2 separate processes going on. You chose one sample from here and one sample from here. And we'll see later why we want that third set. So here I just created 2 independent sets to keep things simple. And so our basic process, we want to use a linear regression and the ML regression. And so you want to read the training data. We're going to create a linear regression object, give it some parameters, and then we want to fit the regression object to our training data to get a regression model, and then we can read the data we want to run the model on, and then we can evaluate that data using the model and see the results, right? So that's what we want to do, is just first read the training data, create a linear regression object, train the object, and then we can then see the results on our test data. Well, reading the data, if it's already in that format, Spark knows about that format, so you just read it in. And this is what you get, right? It automatically declares features and label, right? Which is nice because that's what the model is going to expect to look for. And it also creates, the features are a column of vector of doubles. I'm not sure. So the first element here is basically how many entries there are. The third one is entry. I'm not sure what the second column is for in that format, and I didn't look it up. Right, and that's the file I read. That's what we get. Now we need to fit the data, right? So I read the data. I create a linear regression object. There are a number of parameters we can set. I set the max iterations. Depending upon what the data looks like, the algorithm has to iterate several times to try and fit it. Given the data we're reading, it's not going to be a problem because it is exact data, right? So it's only take one iteration. And then there's a fit method called on object, and it returns a linear regression model. That's it, right? So again, all the algorithm is hidden from us, right? And then we can start looking at the model. And so one thing we can do is ask for its coefficients and intercept. And you'll see that it wasn't quite exact. It says a coefficient is, well, it's almost 1. I mean, it floats, right? I mean, how much closer do you want to get to 1 than that, right? And then, of course, the intercept should be 0 because it was just x, right? And that's pretty close to 0, right, for a float. I mean, you don't get much better than that. So now we have our model, right? We can also, there's other information we look for. We look at the residuals, right? How far off we are from the problem, of course, is, yeah. And then we can get the root mean square error, which is basically you sum up all the residuals and square them to get the negatives. And again, that's very small, but you'd expect that because this is a straight line. And we can also get R2, which is basically the Pearson's correlation coefficient squared. When we start adding more independent variables, what R squared is changes a little bit. And it's telling us that, which is good because we're dealing with basically a straight line, right? So now, how do we use the model? So I read my data, and then there's an evaluate method on the model, which you pass in the data. We get back a linear regression summary, and there's various information we can get from that. We can get the predictions, and what the predictions do, it gives us a data frame which shows us here's the label, right? Here is the features, and here's what was predicted given the model, right? And of course, you'd expect the predictions to be pretty good. So it predicted, 49.999, and the actual value was going to be 50, right? Now, the one thing that's going on here is we really only wanted to give it the we really didn't need the labels, right? We just wanted, here is independent variable, give us the value of the dependent variable. But file format gave us both, so right. So it's and here's the entire program, right? Where so it's a very you just read the training data, right? Create the regression object, train it, do a fit on the training data, and then we can call evaluate on the data we're interested in, and then we can start looking at the model. Simple, right? What's that?
Do it on the assignment.
We can also, once you've created a model, we can also save it to disk so we can reuse it. So we don't have to train the model every time. So you might have, training data, you train it, and then we're going to use that in production. And so when you get the model, we can just call write and then save and give it a name to save it to. And when you do that, you get, multiple files. And then, of course, if we can save the model, we need to be able to read it back in, right? So so there's a method on the linear regression model object, because Scala doesn't have class methods on, right? To load, and you give it a name and it loads it in, and now you can use it.
The model is line.
The model is just a line in this case, yes.
And so all of its predictions can be unlocked. They have the model.
But yeah, what we're doing here is we're doing linear regression, right? And linear regression means here's a line, right? So what we're assuming that our data is a linear process.
So I'm just wondering, the predictions is yeah, just a line or similar type of data.
No, the model is just a line.
Oh, okay. So, well, it seems like really variable. I'm mistaken, because it seems like you can only really compare like this thing to that thing. Run it up against like 5 or 6. Yeah, and how would that be represented?
So there's several questions, right? How do we handle more than one independent variable? This code will handle as many independent variables as you want, right? And we'll see an example of that a little later on, although not with linear regression, with a logistic regression. And then when you then print out the coefficients, you'll get a coefficient per independent variable, right?
Those.
Why? and literally, when we're using this format, you would just have a space, then a 2, then a colon, then the value of that second variable, right? So if you wanted 30 independent variables, not a problem, and that happens a lot, right? And I forget, I think Spark, I did read this. There's a limit on the number of independent variables you can have, but I think it's like 1 million or something. I mean, now what does happen, right? Here we're just looking at, it's just an equation, right? F of x equals a times b times a plus a times b times x, right? When you've got 5 independent variables, you're looking at 6-dimensional space, right? And now we're trying to make predictions on that. And we're basically trying to predict what that equation is. And so we're going to need a lot more data to get it accurate, right? Now here, I didn't have much data, but I didn't need much data for 2 reasons. One is just one independent variable, and secondly, the data is exact. There's no randomness, right? In the real world, we're not going to get something that's nice, right? Some values are lower, some values are higher for some reason. And the more variance you have, right, the more data you need to get a more accurate line. Now, if you're in a 5 or 10-dimensional space, each time you increase the number of dimensions, you need more data, because your data, if you have the same number of data points, if I got 1, 2, 3, 4, 5, 6, 7, 8, I got 9 data points, right? If I'm in a 9-dimensional space, and I only have 9 data points, you almost have no information, right? So that's yeah. So the more individual variables you have, the longer it's going to take. There's also we then have to worry about how many iterations you want. We can also set things like the tolerance. As this thing is iterating, at some point, well, it'll start presumably converging on an answer, but the closer it gets to an answer, the slower it's going to change each time. Yeah, so at some point you say, well, look, it's good enough, right? So we set a tolerance, say when the changes are all less than this tolerance, you can stop. Otherwise, it could spend hours just making minute changes, not really affecting anything, right? Now, how to visualize something in 5-dimensional space? There's a problem, yeah. Space, yeah. Yeah, when I was an undergraduate, there was a group, I forget where they were, making movies of n-dimensional objects, and right, it was sort of fun to watch them, because you start doing slices, like you take a 4-dimensional object and show it in 3D space, right, 3D space. Right, so this is just basic doing linear regression, right? And then we can save the model, reason the model. Okay, now what do you do if, our data looks like that, right? How do we then read that data and convert it so we can use it in the regression models? And there's a couple transformers. Spark comes with a lot of different transformers, and we'll spend more time looking at them. One is called RFormula, which is used in R, so that was a great idea. So they implement it here. What they call a VectorAssembler. So we'll look at both of them, and look at the VectorAssembler first. And basically, what it does is it merges a bunch of columns into a vector of doubles. And so you just create the assembler, and you tell it, here's the input columns I want to use, and here's what I name the column, output column, and then you can transform it, right? And so here's an example of doing it, where just I want to read in a table, and here I'm doing it using explicit schemas, because at one point it was guessing the wrong schema, so I just decided to specify a schema, and so I read the data, and I can then basically say input column is going to be, in this case, just X, because I only get one independent variable. The output put features, just because that's what the model expects by default. And then I transform, I get a new data frame, contains the original data frame, and then the feature, right? Right, and that was my input. And again, if we had 5 independent variables, and each individual has its own column, and then I just, in that array, I list all the columns I want, right? So now we can read, right, more normal, comma separated, whatever column data we want, and then transform it into what the model expects. Right? Again, pretty simple, right? But I didn't change, there's no label, right? And the model is going to expect a label, but it turns out in a linear regression model, we can tell it what the input, what the independent and dependent variable columns are going to be. So in this case, right, when I create my linear regression object, I can say, okay, the label column is going to be Y, not label. And we do the same thing with features, right? We don't have to use the default value. And then, right, I mean, the example is too simple. I mean, you have to be more complicated one. So here I had two independent variables, and then I added some randomness, right? Just so that data wasn't so fixed. And so here's my data. Right, so now we can try and get the linear regression model of two independent variables. So it's not going to be a line anymore. It's going to be plain, right? But it's, you know, it's straightforward, right? I mean, again, I have to read the input. So my schema, I then, you know, use the vector assembler, and I give it my two independent variables, and then there's my feature set, and you know, I can then look at the coefficients. Like I said, you get two coefficients, one, right? Well, we have to ask which column came first. Oh, X came first, right? And so that's the coefficient of X, and that's the coefficient of Y. And so that's basically our equation, right? It's now f of X comma, what I call it, Z, right? It's going to be, you know, 1.07 times X plus 1.1899 times Z plus 9. And actually, you know, R squared is lower, which you'd expect because we're not have exact data. And obviously, we sort of look at the actual data process we started with, we're a bit off, right? Because you'd expect, well, the intercept should be 0 approximately, but it's saying it's almost 9.4. And it's saying the coefficient of X is close to 1, and the coefficient of Z is also close to 1. Right, so there is clearly more randomness and also a very small data set, right? Presumably, if we had, instead of the 20 I had, where it was, I had 20,000, hopefully we get closer to our underlying function. So far, so good. The other way of converting, which is to use the RFormula, and they have this sort of syntax we use. So y twiddle xz basically tells the model that, oh, my dependent variable is going to be y, and I'm going to have two independent variables, x and z, and what I want you to do is I want you to model that equation, y equals a times plus b times x plus c times z. The -0 or +0 says do not include the intercept, and the colon means multiply those two independent variables together to get another term. So then what we do is we figure out how we want what the model to look like. We can describe it using this, and then we can use the RFormula object to then transform to create the features for us, features column. The question is, does Spark use the GPU or the CPU to do the machine learning? I believe they just use the GPU. So when we're doing linear regression, logistic regression, that's okay. When we come to neural networks and deep learning, you probably that'll be a problem, right? So far, so good on RFormula. So how do we use RFormula here? Well, again, I'm going to read the data, create an RFormula. I set this formula. In this case, I only had one independent variable, and so the formula is this y twiddle x. And then it's a two-step process to get the actual data frame we want. One is we have to fit the formula to the data, and then we can transform it. Before we transform it, it doesn't know what the columns are, what the data types are, has to figure out how to deal with it, and we transform it. And by default, it creates a column called features and another one called label. All right. And again, that's a default you can change if you want. Now we can, two independent variables, right? It's just the formula is going to be y twiddle x plus z. And then we fit the formula and we transform the data, and then that's the output. Questions so far? So we know how we can do linear regression. We've got several ways. We can use SMV format for the data, or if we've got regular columnar data, we've got two ways to transform it into what the model needs. And so, yeah, multiple linear regression basically means you've got more than one independent variable, and that happens all the time, right? And as someone pointed out earlier, it becomes hard to visualize these things because they're n-dimensional. And when you try and doing it, like here, here's an equation with two variables, and you try and plot it on a, it looks like there's some randomness. There's a band here. Well, that's because you're taking a three-dimensional space and you're flattening it down a two-dimensional space, right? So it becomes hard to visualize these things. So then we can start looking at, instead of visualize them and saying, oh, this looks like a straight line, that's pretty, we could start using statistics to tell us, and we've got this r squared. The problem is that r squared has a very odd property that you have to be careful of. And that is, when you add more independent variables to the data, r squared increases. So it makes it look like it's getting better. It doesn't matter if those independent variables have anything to do with the model at all, right? You can just add random data to random columns, right, as more independent variables, and when you compute r squared on it, it's going to go up. And this can cause a problem in that, is my model better? Well, r squared is higher, right? So it has to be better. Not necessarily, right? The statisticians have what they call adjusted r squared, which handles this a little better, but Spark doesn't compute it. It only computes the regular r squared. There's machine learning. They have what they call hyperparameters, which sounds pretty fancy, but it's just a fancy word that means these are parameters to the algorithm which the algorithm can't learn from looking at the data. They won't affect, right? So the name of the feature column, the algorithm can't figure that out, right? So it's a hyperparameter. The name you give the label column, it can't be figured out. How many iterations you want, the maximum iterations you want the algorithm to do, that's something we set before we start training, right? The convergence tolerance, that is, when do you say, okay, you're making so little progress, just stop, right? The column weight, that's at each, how much weight to give to each row, not each column, right? There may be times when you look at your data set, right, some data may be suspicious, so you want to give it less weight. And then there is this elastic net parameter. Like, what is an elastic net parameter? And it's pretty weird. So the algorithm is trying to figure out how to estimate these coefficients. And there's two of them, and they're called L1 and L2. Why? Because someone, many years ago wrote a paper on these algorithms, and they said, we're going to do it this way or that way, and they call this one L1, they call this one L2, and the name stuck, right? And so unless we go back to that paper and read what the algorithm does, so the L1, the goal is try and shrink a lot of coefficients to 0, right? And then you get few coefficients which are non-zero, rather than have a bunch of them are close to 0. So okay, if they're close to 0, just set them to 0. And L2, right, it doesn't do that. So you might get lots of coefficients that are close to 0. And so we have this parameter which we can set. Do we want to use L1 or do we want L2? For better or worse, it's not just use A or B, it's use, we can say, well, I want you to use L1 20%, we weight it 20%, and then we weight the other one 80%. So we can tell what weight we want to use for each one. Right? Which leads us to then, how do we choose these hyperparameters? I mean, it sounds like the name of the feature column, that's trivial. We don't worry about that. But there are other of these hyperparameters which will affect the algorithm, and how do we then set them? It might be you have some knowledge of the data and say, okay, for this data, it's appropriate to use this hyperparameter, right? But that requires knowledge of the data. It requires domain knowledge. Also, probably means your statistician or mathematician has done this a lot to understand what forces, right? We can experiment with the data, but now you have to be careful. Here's where you may want to partition your data set into 3 pieces. One piece to use to sort of train your hyperparameters, and another piece to train the model, and another one to test the model. And here's where we have to warn you about overfitting. Yeah, we'll see grid search a little bit later, probably not today, but how it'll do some of this for us. Overfitting is dangerous. The best way I know to describe this, when we just do too many one way to overfitting, you just have too many parameters. The way I always try to explain it is, we know if you've got 2 points on the plane, right, we can fit a straight line, right? If you've got 3 points on the plane, we can always find a quadratic equation which go through those exactly, right? So in this case, we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. There's 11 points. So we can always find a polynomial of degree 10 that'll fit these points, go through these points exactly. That may not be the equation you want to use to model what's going on here. Why? Because you may get things like this, where to fit them exactly, you got these things that oscillates wildly, and clearly this is not modeling those data points, right? Data points, a couple of these points are sort of outliers, but a lot of them are pretty linear, right? So if we've got n data points, we can always find an equation which will meet those endpoints exactly, but you may get weird things in between which don't model what's going on with your data at all, right? And the same thing with machine learning. We can always, if we add more parameters and twiddle with them, we can keep on increasing how close our model gets to that data set, right? But the problem is, when you then go to a different data, right, you may land in points where you've done this crazy thing to the equations, right? So you really have to be careful about not to overfit the data. another example, here, right, you have a bunch of data points and red and blue, and you're trying to classify them into two groups, right? And again, we can draw a line to do it exactly, right? But that line is probably overfitting, and it's probably not a good one to use, right? And, so that curved line is probably a better line to use to separate the two into two groups, right? Right, so you have to be aware of overfitting the data. And again, we're computer scientists, we're not mathematicians, right? So in a lot of these algorithms, we need deeper knowledge of the algorithms to know when we're doing that, but you should be aware of the problem. Okay? Now, we had linear regression, right? Which you're basically doing a line or a plane or hyperplane. But there's also called generalized linear models. When you're doing a regression to other distributions. And there are a number of common regressions that you can do. Spark does have a general linear models we can use. The one I want to look at is logistic regression, right? And that's interesting because there's only a finite number of outcomes. Instead of having this infinite number, you have finite number. And that's what they call a categorical variable, where there's only a limited number of fixed possibilities. So examples like blood type, right? We may want to correlate that with something. And there's only a fixed number of blood types. The political party you're going to vote for, I mean, in this country, there's a fixed number, right? The state you live in, we only have 50 states. And the problem is, right, the linear regression assumes that there's a formula there, and that doesn't work when you have finite outcomes. And if there's only two outcomes, the standard way to model it is 0 and 1, right? And so logistic or Logit regression handles the case when the dependent variable is categorical, right? There's a fixed number of outcomes, right? And so let's look at an example of doing a logistic regression. And so I created a fake example where the data is how many hours study for an exam, right? And did you pass or not, right? And well, there's two outcomes. You either pass or you fail. I could have done it ABC, but for example, this is 2, and 0 means you didn't pass, 1 meant you passed, right? And so I created a small data set. Now, when we do logistic regression, there's a bunch of hyperparameters. The family you want to use is either binary or multinomial. That is, how many outcomes do you have? In this case, it's binary, so we use binary. Elastic net, same thing. There's fit intercept. Do you want to have an intercept or not? we can regularize the inputs. I didn't look at the last two. There's training parameters, how many iterations you want, the tolerance again, and the weight column. Do you want to weight certain rows heavier than others? And then there's some thresholds we can use, the threshold you want to use to do predictions. We'll just use the default values. Again, it's a regression model, so we need to have the features need to be in a vector of doubles. So again, it's the same process. We need to read our data set in. And so I read the data, which is straightforward. I'm using RFormula, where past depends upon just hours studied. I then have to, create my data set, and then what I do is I want to divide that data set into a training set and a test set. And there is a random split method on a data frame to do it for us, and we tell it, in this case, I want to use 70% in my training and 30% in my test set. And then there's this weird scala syntax where I can basically say I'm getting back a tuple, and the first one is going to be my training set. Yes, right. And then we can look at the data, and we get the two columns, right? So one label one and the feature. So again, yeah, we're just dividing the data set into two pieces. One is to train the model, one is to test it. Again, when the process is the same, right? We need a regression. Instead of a linear regression, we create a logistic regression object, and we can train it. And we can still get the coefficients.
So a few slides ago, you were talking about R squared and adjusted R
Right.
squared. Are you able to, so any independent random data R value? And then my follow-up to that is, what if we already have random data? Doesn't that make R value?
So the R value, right? Adding more independent variables will increase the R value.
What if I have and one of
Yes.
one of it like random? I don't know that.
Yeah. So what if you have a data set, right? And you've got 25 possible independent variables, right? Yeah. How do we know which one, which variables we want to use in our model? Part of it can happen from thinking about the data and what it means, what possibly could be. We'll see later on. There are a couple of algorithms to try and reduce the amount of data we have. Principal component analysis is one. But yeah, it's more art than science.
Okay.
That's one of the challenges. Yes. The question is, can we weight columns? Not that I'm aware of. I mean,
would it find the correlation already?
in theory, but it also depends how much data you have and how much randomness there is, right? And so, one way it can be done, which is sort of painful, is to, run the model multiple times, right? We don't drop, this time only use these 5, this time we use these 5, we'll lose 10. And then test it on our test data to see how well that model performs. And that's one reason why when you have a data set, you use the same data set to train and to test, but you have to divide it. You take that data set and you divide it randomly into 2 groups so that both your training set and your data set, right, testing set, have the same sort of distribution of data. If you've got a complete training set that's completely in over here and your test set over here, it might be different, have different biases, right, or different underlying processes. So when you then take this test data and then measure to see how well your model does, you may be measuring the difference between the 2 data sets, not the difference in the models. And that's why there's a built-in function to, here's my data set, divide it into a training set and to a test set. And then we can generate 5 different models and see how well they do on our test set. But this is becomes less precise than you would like. Right? It's, then we can actually evaluate the model on our test data, and we can also then get the predictions and show it, and it shows us, right, the data frame we inputted, and then it gives us raw predictions, and it gives a probability, and basically probability of 0.5 or above goes, in this case, to 0, and below goes to 1, and you start to see, well, on this particular data set, right, they pass, but the model said they will fail. But the probability is 0.51, and so it was pretty close, right? But there has to be some sort of cutoff that says, okay, whereas, these 2, right, the probability that it should be a pass was fairly strong.
Is that probability of failure? Is that why is the number so low?
Oh, no. What this is, what we're doing is there's a probability distribution here, and we're cutting off at 0.5. And below 0.5 is like they go in group 1, and above is 0.0. Right, yeah. And actually, next slide sort of explains this. In linear regression, we're fitting things to a straight line, right? So the equation is a straight line. Here, we're modeling things on what they call a logistic function, which is, I thought I had, well, it's basically a function that looks like this, right? And the equation basically is 1 over 1 plus exponential of the intercept times the coefficient times your independent variable. And so all these probabilities are just, you plug into the equation and it's telling you where you are on this. And once we hit 0.5, we go one way, above it, go the other way. And then we can start doing various things like changing what point we want to switch from one group to the other group. Yeah, I'm not sure what, that's the actual logistic equation that we're actually fitting. And this turns out to be very important when you get to neural networks. They use this as one of the functions that each neuron will use to train itself. And yeah, that's so all these predictions are just basically, all they're doing is this model is computing these coefficients, and then these predictions are just evaluating that equation. So next time we'll look at some more examples of doing logistic function regression. And you may have some questions about your assignment because the description is going to be a bit longer because we actually have real data. Okay?